Okay, so I'd like to start off by roughly explaining what space weathering is, but for the sake of time, all I'll say is the surfaces of airless bodies are exposed to high energy interplanetary environment that results in chemical and structural alteration of regolith that's at the very surface of the moon. I'm interested in only a couple of those features. So this is a lunar northite that was embedded in epoxy, sliced at 50 nanometers thick thin section and stuck in a TEM. This is a bright field scanning transmission electron microscopic image. The feature I'm interested in is on the very rim. So if we look at the dark field stem image on the right, we'll see two notable features. One is a solar wind damaged rim that forms through low energy solar wind, primarily hydrogen and helium ions that penetrate nanometers beneath the surface of a grain, resulting in this layer of ionization damage. And then we also have solar energetic particle tracks, which form from higher energy solar energetic particles, mostly iron group nuclei that can penetrate millimeters beneath the surface, leaving behind these tracks of irradiation damage. Both of these features accumulate with continued exposure on the surface. So recent work by Keller et al. 2021 used modern TEM techniques to observe high track densities. He was able to observe 10 to the 10, 10 to the 11 tracks per centimeter squared, and was able to develop an updated track production curve shown on the left. And with this, they were able to determine a track production rate of 44,000 tracks per centimeter squared per year. The figure on the right shows the relationship between solar wind damaged rim width and track density and exposure age. And as you can see, this is for lunar northite. Those are the red triangles you see. You can see that over the course of about 10 million years, the rim width increases quite quickly before leveling out. However, the track density continues to increase with continued exposure on the surface. So with this new method to identify exposure ages on individual grains, I wanted to apply this to 73002. So we've all seen these figures before. Yesterday during the stratigraphic session, they were talked about a lot. So on the left, we have an image of the core. We have our dark and our light lithology. That dark upper region is the space weathered material. And it's confirmed via optical maturity profiles and ISO-BEST over FEO profiles, just showing that there is space weathered material that extends several centimeters beneath the surface. So I'm looking at how space weathering is from the perspective of individual grains. I'm trying to identify the exposure ages of grains distributed throughout the core, specifically in the in situ reworking zone, so those upper few centimeters where the space weathered material is most prominent. So Purdue received material from JSC. We got the top 8 intervals of the top 4 centimeters, and then every 4th interval following that. We got them as sub 45 micron size fractions, but from ultramicrotomy, we wanted sub 20 micron size fractions, so we dry sieved the material, embedded the material in epoxy bullets, sliced them at 50 nanometer thick thin sections, stuck them in a TEM, and took bright field and dark field stem images. We counted tracks within half micron of the grain rim, and then we drew 100 by 100 nanometer square areas around the densest regions, extrapolated that out to per centimeter squared, and then used the production rate of 44,000 tracks per centimeter squared per year to determine our exposure age. And then we directly measured the rim width using digital micrograph analytical software. We restricted our analysis to northite and olivine grains, as those are the most well constrained for this kind of work. And we identified those grains using energy dispersive X-ray spectroscopy. So far, we've looked at 30 grains from interval 1 and anywhere from 5 to 15 grains in intervals 2 through 8. The majority of grains have exposure ages ranging from 1 to 5 million years. The oldest exposure age was 11 million years. That was found in interval 1. The second oldest exposure age was about 8 million years. and that was found in interval 6, so 3 centimeters beneath the surface. In relation to the work of Keller et al. 2021, we find that our results align very well with that upward trend where we see increasing rim width with increasing exposure, that area circled on the figure. This is just a histogram of interval 1, just a different way to look at what I just showed you. We can see that there's a peak ranging from 1 to 2 times 10^11 tracks per centimeter squared, corresponding to 4 to 5 million year exposure age. And then grains with higher densities are increasingly more rare, less common. When we combine all of the intervals, we see a similar trend. Again, track densities corresponding from 4 to 5 million years of exposure, with increasing densities being more rare, less common. And then we have a couple of examples of the track densities we've observed in the TEM. So the center image has a track density corresponding to 3.48 million years of exposure. And then we have our highest track density grain on the right, which corresponds to 11 million years of exposure. Also, might want to note that the rim, the solar wind damaged rim thickness is much larger for that older exposure age grain than the one that's only 3.4 million years. So to conclude, we find that surface exposure times in the in-situ reworking zone peaks at about 5 million years, and so grains don't really hang out on the surface for that long. It's testament to the high rate of overturn at shallow depths on the lunar surface. We see similar distributions with depth that suggests there's some approaching homogenization within the reworking zone. And that was described, it was McKay in 1974 was one of the models that was mentioned. And the oldest exposure age of 11 million years is within range of the reworking timescales that was mentioned by Dick yesterday during the stratigraphy session. I think it was the highest exposure, the highest reworking timescale was about 17 million years, and 11 million years is kind of right in the middle of that. Anyway, that's all I have. So thank you for your attention. I'll take any comments or questions.
Questions? That's some spectacular data that makes crystal size distributions look really easy when you're tracing these tracks out at the nanometer scale. The precision of your exposure ages, you get down, you got 11.14 million. What's the, do you calculate an uncertainty on that, and where's that uncertainty come from?
So,
right, and that's where I was headed, but Darby's ahead of me as always. So, because you've got that histogram there, are they distinct or are they within uncertainty, within error?
So, roughly speaking, the uncertainty is within a few 100,000 years, more or less. It's something I need to think about more. This is just kind of a rough estimate of where things are. I need to look at more grains. So I haven't looked at enough. I've only looked at 30 grains, interval 1, and then not as many grains in the remaining intervals. So yeah, it's
just, you quote to 2 decimal places on your million-year time scale. So that was why I was thinking, wow, these are getting quite precise. So just to sort of want to keep that in mind. I think that's something to look at closely, because if you can start delineating these, it could represent different reworking events or different impact events.
I'll keep that in mind. Thank you.
Lindsay?
Yeah, along those lines, there's in the calibration curve that we developed last year, there's an error on that track production rate per year. There's an error associated with your track counting depending on the track density and things. Your histograms are real. I mean, the errors are smaller than these 500,000 year intervals you have. So that's totally fine. But yeah, your precision, you can quantify that.
All right, any other questions? Thank you very much, James.